Okay, so with that, I'll welcome all of you to this first of two sessions on extreme precipitation, past, present, and future. My name is Neil Tandon from York University. I'm joined by my co-conveners, Megan Kirkmeyer-Young from Environment and Climate Change Canada, John Jackham from McGill University, Xander Wang from University of Prince Edward Island, and Mohammed Shah from University of Prince Edward Island as well, who will be assisting me with co-chairing this session and moderating the question and answers. So yeah, I think this will nicely complement a lot of the great sessions we had last week, focusing on British Columbia and give us a sense of the bigger picture of extreme precipitation in Canada and beyond. So with that, we're at 10:25. Do we have Chao Li on the line, who will be our first speaker? Chao Li from East China Normal University. If you are there, you can share your slides and take it away. So I don't think we have Chao yet. So we will take a breather, I guess, till Chao arrives, just so that we stick to the speaking order in case anyone's joining from other sessions who might want to see the other speakers at their scheduled times. So we'll see when Chao shows up. Just a question to the CMOS volunteers in the room. Were you given slides by Chao that maybe we could load in the meantime? I know that was optional for them to send in their slides. So just a note to anyone who's just joined, we are still waiting on our first speaker. So we will get started as soon as our first speaker arrives. Unless any of the first speaker's co-authors would like to speak on the record.
Yeah, I'm sorry, I don't have a set of Chao slides. I'm one of his co-authors.
Okay. So we will be handling all question and answer through the chat initially. So if you do have questions that pop up during the talks, you can post those in the chat. And one of the chairs will read those off at the end of the talk. And yeah, if nothing comes up in the chat, we can prompt you to raise your hands and speak up as well. Yeah, I appreciate that, Anas. I think we're going to stick to the schedule just in case others are, people are jumping in between sessions. All right, again, we're just waiting on our first speaker, so sorry for the silence here.
Neil, did you see the chat? He's trying to connect.
Yeah, I saw that message. Yeah, thanks, John. So we'll see. What we maybe can do is, because we've got that 5-minute space in the middle of the session, we can see if Chow is able to log in soon, then we can kind of shift things by 5 minutes. All right, so at this point, I think anyone who would likely be logging in for Anas's talk would probably be here already a few minutes early. So if Anas, you're all good to go, we'll go to our second speaker, Anas Ali from York University. You can go ahead and share your slides and take it away.
All right, sorry. Let me just make this full screen. Everyone can see this, right? Full screen?
Yep, looks great.
Okay. All right, so hi everyone, my name is Anas. I'm gonna be talking a little bit today about some of the work I've done thus far in my master's thesis. The topic of which is the influence of horizontal model resolution on the spatial scale of extreme precipitation events, right? So before I can get into the methods and then ultimately the results of the work we've done thus far, I think a little bit of background is obviously necessary, and the best place to start for that is with a quick reminder of why we study extreme precipitation. And a big reason we study extreme precipitation is because the consequences of these events, right, extreme precipitation events, can be pretty severe. And a good example of that is the Alberta floods of 2013, and you can see a photo of the aftermath of that on this slide right here. And this was an event that was caused by heavy rainfall due to an extreme precipitation event, right? So it's a good example of why we study extreme precipitation. If we're not prepared for them, if we're not prepared for these events, the consequences can be pretty severe. So one thing that's well established in the field is that if we want to study extreme precipitation intensity, we have to really study what influences it. And the main thing that influences is extreme ascent, which is just the vertical velocity that's associated with extreme precipitation events, right? Due to the upward motion of air. But if we want to study this extreme ascent, what we really have to study before that is the horizontal scale of ascent. So this sort of gives us a three-step process, right? First, we study the horizontal scale of ascent, then we can study extreme ascent, and then ultimately we can study extreme precipitation intensity. But this sort of begs the question, right? What's the main tool we have to study these horizontal scales? And the main tool we have for that is model output. Using model output, we can actually compute these horizontal scales and actually do our research. But this begs the question that is present whenever we use models, right? Are models suitable for this application? What are the differences between models? And my thesis in particular asks, what's the influence of model resolution upon these horizontal scales? So after establishing this question, right, how did we actually go about answering it? Well, the first thing we did was download a bunch of model data, right? So we used models in the CMOS project, which stands for the Coupled Model Intercomparison Project, Phase 6. And we used roughly 13 models. So all the data that you'll see today, right, all the plots I show you will include 13 or 14 models. And we defined extreme precipitation for our work using an annual maximum of daily precipitation in a one-year return period. So as we know, there's several ways you can define extreme precipitation, right? You can have a percentile-based approach where you say, I'm only going to look at the top 10% of precipitation events, and I'm going to use those as my extreme precipitation events. Or you could have like an absolute threshold where you say something like, I'm going to use events that have more than 100 milliliters or millimeters of extreme precipitation. I'm going to use that as my extreme precipitation events. What we used was an annual maximum, which corresponds to something like a 99.7 percentile approach. And for the temporal considerations, we used a 20-year mean of 1981 to 2000, which mainly we used to facilitate comparison with other work in the field. And if you're not familiar with horizontal scales, a quick schematic of that is on the plot here on the slide. So you could have some value like P naught, like your initial precipitation. You want to see where it decays to 1 over E of its value. And the distance it takes for you to get to that is what you refer to as your E folding distance. And after scaling that by some coefficients, you can get to a horizontal scale, right? Which you can, average over multiple cardinal directions to get like a better idea of what your general horizontal scale is. And using this approach, we computed the horizontal scales for various quantities associated with extreme precipitation. So the first useful result I can show you is, the length scales for precipitation, which is what the top plot is here, and the length scales for vertical velocity, right, which is just extreme ascent, which is the bottom plot here, for one particular model. So in this case, the ECR3 model. The conclusions are the same for any model that we've looked at, but I just picked this because it had a pretty high resolution. So the first thing you'll realize is that the spatial scales for these two quantities, they sort of follow what you expect for precipitation events, right? There's minima inside continents and there's greater values elsewhere, right? Like along coasts and over the ocean. And that's what you see for both quantities here. But you'll also notice that they have somewhat different magnitudes, but they're still the same order of magnitude, right? The precipitation length scales go from something like 0 to 350 kilometers, whereas those for vertical velocity went from something like 0 to 500 kilometers. So it's the same order of magnitude, but still somewhat different. But the key takeaway here you can take from this comparison is that there's a very similar spatial distribution for both vertical velocity length scales and precipitation length scales, especially if you look around North America, across Central and South Asia. There's a lot of complicated structure that both length scales capture correctly or similarly. But what happens if we look at geopotential length scales, which is what's the bottom plot here? The top plot is the same as it was on the previous slide, it's just the precipitation length scales. And the main reason we're concerned with geopotential is because it's related to pressure. And pressure, of course, impacts the wetness or dryness of the weather that you would expect, right? So high geopotential is related to high pressure and dry weather, and the opposite is true for low geopotential. And something you'll notice from this comparison is that the magnitudes are completely different for geopotential length scales, right? They go from something like 0 to 2,000 kilometers on this plot, and there's some extreme values that go as high as 5,000 kilometers. You'll also notice that there's completely different spatial structure when it comes to geopotential length scales, right? The high values for geopotential are clustered right along the equator, which is completely different from that of the precipitation length scales. And a key takeaway from this is that the large scale dynamics that we associate with geopotential, things like the Lahadi circulation, they do not constrain length scales when it comes to extreme precipitation events, which we can clearly see from this comparison. Another useful result I can show you is the zonal means of extreme ascent for various models. So that's what you see here. So the x-axis is just different latitude bands, and the y-axis here is the mean extreme ascent length scales in kilometers. And what you'll notice very quickly is that all the models have similar behavior, right? There's a peak at the equator and there's a peak at each pole. However, there's a large spread in the magnitudes between all of the models, right? So this sort of indicates that there is indeed a difference between the models, and we should, do some further study. And in particular, we're going to look at the 70th to 40th range, right? The subtropics, primarily because that's where a lot of the work has already been done in the field. So when it comes to, actually answering the question of the thesis, right? What's the influence of model resolution on the spatial scales, right? This plot is something like the key result that we have, right? And it's a scatter plot of the mean horizontal scale of extreme ascent versus the zonal resolution for various models, right? And what you see here very clearly is that there's an upper limit placed upon the model resolution, or placed upon the model's length scales for extreme ascent that seems to decrease as your model resolution increases. So there's something like a downward trend on this upper limit. And this is very clear here when we plot the mean length scales of extreme ascent. But what happens if we do the same thing for the precipitation length scales? So that's what you see on this slide right here. So this is what the precipitation length scales look like versus the model resolution. And again, you see the same behavior, that there's an upper limit that's placed upon the model resolution, or placed upon the model length scales for precipitation that seems to decrease as the model resolution increases. However, you can also separate precipitation into two different portions. You can separate into a grid scale of precipitation, something that you refer to as PRL, and a subgrid scale of precipitation that's associated with like parameterized convective effects, something that we refer to as PRC. So what happens if we look at just the contribution of the grid scale of precipitation? Well, you see that the length scales here follow a behavior that's very similar to that of the total precipitation and the extreme ascent length scales, right? There's an upper limit that's placed upon these length scales for precipitation and grid scale of precipitation that seems to decrease as your model resolution increases. But what happens if we look at sort of the sister component of this, the subgrid scale level precipitation that's associated with the parameterized convective effects? So that's what you see on this slide right here, the parameterized convective precipitation. And here you really don't see any influence of model resolution at all. There's no clear influence that you could draw here. So the key takeaway that we can take from this comparison of the grid scale and parameterized convective precipitation is that the model resolution effect is mostly associated with the grid scale of precipitation rather than the parameterized convective precipitation. So in just a few plots, those are some of the key results that my work has shown thus far. And I'll just summarize them really quickly on this conclusion slide. So if you go back to those global plots that we had from the ECR3 model, what we saw was that the length scales for extreme precipitation and ascent were very similar for each model, both in magnitude and in spatial distribution. And again, this is something we physically expect because because extreme ascent influences extreme precipitation. So we expect their length scales to line up in some way. However, when we looked at the length scales for precipitation and for geopotential, we saw that they were very similar, both in magnitude and in spatial distribution. And what this shows us is that the large scale dynamics are not constraining to precipitation spatial scales. Stuff that we associate with geopotential, like the Hadley circulation, isn't constraining spatial scales here when it comes to extreme precipitation events. When we went to those scatter plots that showed model resolution versus the length scales for different quantities, what we saw was that the length scales for extreme precipitation, grid scale level precipitation, and extreme ascent all had upper limits that were likely influenced by model resolution. And that influence appeared to be a decreasing upper limit on the length scales as your model resolution increased. However, when we looked at the length scales for the subgrid scale level precipitation, the precipitation that we associate with local convective effects, and the length scales for precipitation, or for geopotential, sorry, that those were not clearly influenced by model resolution. So we couldn't have the same conclusions there. So those were some of the results that we had thus far. What are the next steps, right? So obviously, observational comparisons are something that you have to do anytime you use models, right? You want to make sure that the models are giving you results that are comparable to what your observational data sets show. So that's something that we still have to do in our work thus far. And another important thing we have to look at is other factors that influence length scales. So for example, one of the things that we've been looking at lately is the magnitude of the quantity and how that associates with the length scales of that quantity. So something like if you have a very high value of extreme ascent, how is that related to the length scales associated with extreme ascent? So that's something we'll be looking at as well. And another thing that we'll be looking at is different time scales, right, for the resolution. So we've looked at daily resolutions data thus far, but there's also some models that have hourly resolution data. And we want to make sure that, using daily resolution doesn't, hide any results or hide any conclusions, because you could have a day where you have a few hours of extreme precipitation, but otherwise the rest of the day is very dry, right? So that might introduce some masking to the extreme precipitation events. So we also want to look at some hourly data, even though we've only looked at daily data thus far. So those were, some of the results of the work I've done thus far, and some of the next steps that we have. Thank you for listening to some of the work I've done, and I'll be happy to take any questions now.
Great, thanks, Anas. So, Mohammed, did any questions come up in the chat that you'd like to read off?
Yeah, thanks, Ali. I think Mr. Sam Anderson, he asked one question. I can read it out, or you can also see in the chat.
Yeah, you can go ahead and read it off.
Okay, so if you show that these average length scales have upper limits that are influenced by model resolution, is there also a relationship between the variability of this length of a scale and model resolution?
So that's a good question. That's something we might have to look at in the future. But so far, what we looked at was the means in this, over that temporal range in that 70s to 40s range. So yeah, indeed, there could be something that you could study, like what's the variability, but we really haven't done that thus far. The main conclusion we have, again, is that just that like upper constraint conclusion that we've shown, which again, I'll just flip back to. So that's the main conclusions that we have thus far. But I'm sure that there is definitely, useful work that we could do in looking at the variability and how that's related to model resolution. But in so far, we've just looked at, means and how those relate to upper limits on the spatial scales.
Okay, thanks. I think there is another question from Michael Morris. Have you done comparisons for a single model at varying resolution? Looking across different models may introduce difference due to different parameterizations in addition to different resolution.
So we've done that to some level. For example, if you look at this slide, I'll see, if you look at like the INM CM4-8 and INM CM5-0, those are two versions of like the same model, right? There's also some other models that have several different versions that have differing resolutions, right? So the CESM2 models, a couple of them have different versions that have different resolutions, right? So we've looked at it in that sense. There's different versions of the same model that have different resolutions. But in terms of manipulating the resolution of a single model, we haven't done that thus far. We were thinking about some methods of, for example, degrading the resolution of a high resolution model. So bringing that down and looking how that changes the horizontal scales we compute. But that's still work that we have to do.
Yeah, so I guess on this plot, if you looked at the CSM2 FB2, it's in the upper left corner. So that would be the 2-degree version of that model. And then the CSM2 without any tag added onto it would be closer to the right-hand corner. That's a 1-degree version, I think, the default standard configuration there. But yeah, I mean, that's just one small subset. And yeah, I'm sure there's a lot more that could be done in terms of particular models.
Yeah, thank you. I think we don't have any question anymore.
Yeah, were there any others that wanted? We've got maybe another minute if any others wanted to raise their hands. Okay, I'm not seeing any other questions. So thanks very much, Anas. You can stop your screen sharing and we can proceed to the next speaker for the session, Megan Kirkmeyer-Young from Environment and Climate Change Canada. You can go ahead and share your slides and take it away.
Okay,
Everything
great.
looks
Thank
good.
you.
We have our full screen, so go right ahead.
Excellent. Thank you. All right, today I'm going to talk about using a model comparison to support the interpretation of event attribution for extreme precipitation. And this is work that we just recently published in Weather and Climate Extreme that I was working on with Hui Wan and Jubin Zhang, and we're all from the Climate Research Division at Environment and Climate Change Canada. Right, so for event attribution is where we determine how anthropogenic external forcing has changed the likelihood or magnitude of a particular set of events. Usually the events we're concerned with are recent, extreme, and high impact. And we generally calculate a probability ratio between two scenarios, a factual scenario that includes human influence on the climate and a counterfactual scenario without human influence. And these typically are coming from model simulations. So as an illustrated example, on the right, you can see two distributions. The red distribution is precipitation anomalies using in the factual scenario with including human influence on the climate. And this distribution is shifted towards higher anomalies compared to the blue distribution, which is just natural forcing only. And if we wanted to calculate the probability of the observed event, that vertical bar, then we get, and the ratio of those probabilities is about 3. And that tells us that this event we're concerned with is about 3 times as likely to occur with human influence than without. So event attribution has been increasing in popularity and recognition. So more and more studies are being done on events using these kinds of methods. And more people, outside of the scientific community are interested in the results of this type of work. So as this happens, it's really important that we make sure that we understand the sensitivities of event attribution and how to properly interpret it. So by interpretation, what I mean is that the context and implications of a particular study's results, how to relate those findings to other analyses of other events, perhaps using different methods, and also how do we explain what this event attribution result actually means to the broader audience that's interested. We already know that event attribution can be sensitive to framing, so how you're, what specific attribution question you're asking, or the different spatial and temporal scales you use to define your event, different methods and so on, and also to model choice, and that's what we're going to talk about here. So our goals are to assess consistency in the attribution of precipitation extremes across different models, and also synthesize this across regions. So we are looking at regional analyses, but on a global scale, and we're providing general and large scale information to aid in the interpretation of attribution for specific studies. So don't consider the events we're talking about here as specific real world events. were the results as 4 specific real-world events, but we're talking more general to help set up the interpretation of event attribution. A quick note on methods, we are using global models. So we're discussing larger scale precipitation extremes. We're using 6 different large ensembles. They're listed here, ranging in size from 16 ensemble members up to 50 ensemble members. And we're using a perfect model framework. So we're taking one realization of this ensemble and letting that act as observations to define our event of interest. We're calculating the probabilities of that event in the remaining realizations from that ensemble. And we can cycle through letting each realization act as the observations to give us a sense of the range. But what's important to keep in mind is that the characteristics of our pseudo observation series and then the rest of the model are all the same. So we've taken out that element, pardon me, of uncertainty. And then we're going to do this for each of those large ensembles and compare the results, the attribution conclusions between the models. Right, so I'm showing you some of those results here. These maps are by grid box, the count of the number of models out of those 6 that show agreement on at least a 2-fold increase in the warm colors or a 2-fold decrease in the cool colors in the likelihood of our extreme precipitation event. If we start in the top left corner, this is looking at the 20-year event in RX 1 day, so annual maximum 1-day precipitation at the grid box scale. So we're calculating probabilities and events at each grid box. We'll see there's quite a bit of gray, particularly over land areas in the northern hemisphere. And this means that the models are not agreeing on a 2-fold increase in likelihood. And this could very likely be because there aren't actually 2-fold increases in likelihood, that the change is smaller and the variability is high. Where there are increases, it is a bit patchy in some other regions. As we move down to the bottom row, we're looking at now 30-day extremes. We see a bit more structure, a bit more agreement among models. And as we move to the right, we're moving from the grid box scale to a regional scale, and we see a lot more agreement amongst the models, a lot more of these pink and red shades when we look at a larger spatial scale. And this makes sense because when we summarize in time or we summarize over space, we're increasing our signal to noise. And that allows us to find these robust changes in likelihood. And I want to know, this is all in the current climate, about 1C warming globally from pre-industrial. If we move to a warmer climate, now we're looking at the same images, but for a climate under 3C of global warming. And here we see much more model agreement. There's a lot more of these pink and red shades. And this shows us that a lot of the models, 5 or 6 of these 6 models, are agreeing on at least a 2-fold increase in the likelihood of precipitation extremes in these cases. And that tells us that the lack of agreement we saw at 1C was probably because of low signal to noise, because as we increase our warming, we've increased our signal, and we do find robust increases in likelihood. And this is probably where a thermodynamic response following Clausius-Clapeyron, where that response is strong. There are regions, you'll know with the shaded blue, where there are model agreement on decreases in the likelihood of extremes. And these are more prominent when we look at the 30-day extremes compared to the 1-day extremes. And these are regions where most likely a dynamics-driven response is counteracting or dominating over that thermodynamic response to warming. And this generally agrees with regions identified by other studies as well. To look a little bit more into these model differences, now these are maps by model of where there are 2-fold increases or decreases in likelihood of these precipitation extremes in the 1C climate on the top row and in the 3C climate on the bottom. So we see lots of gray again at the 1C climate, lots of grid boxes where there is not a strong enough change. There's not a 2-fold increase in likelihood of precipitation extremes at this scale. And where there is where the red boxes are, where there are twofold increases, they tend to be a bit sporadic and patchy and not great agreement between the models. As we move to 3C, we do see much more areas with robust increases in precipitation, the likelihood of precipitation extremes. And these tend to agree better amongst the models, though there are still some notable differences. I want to point out over Western North America, there is some disagreement between the models on twofold increases in likelihood there. And then also these regions of twofold decreases in likelihood, the blue areas on these maps. And while all of these models have these areas of decrease, they're not necessarily exactly in the same place. And why this is important is that particularly when we talk about changes dominated by dynamics, their different models may show similar changes, but with the key features in slightly different locations. And that means that just comparing grid box by grid box won't give you the full picture. And that taking a simple multi-model ensemble average will not necessarily give you a better answer than looking at models individually. Another reason that these models might show us some differences in terms of the attribution and the changes in likelihood is because of the different amounts of data. And in fact, the sample size does matter. So I mentioned we have 6 different large ensembles, and they range in size from 16 up to 50 ensemble members. And to look at how this might matter, we're just looking at the CANI-SM2 large ensemble here, calculating this change in likelihood, this risk ratio, with the full 50-member ensemble, and looking at the uncertainty range on that. And then we're also calculating the risk ratio of the same event, but only using 15 of those ensemble members to calculate the probabilities. And the left plot here is showing you a histogram of the ratio of the widths of the uncertainty range for those risk ratios between the 2 different sized ensembles. You'll see that these tend to be very small. And that means that the 15-member ensemble has a much larger uncertainty range than the 50-member ensemble. And we see that consistently and through the different shades of blue, different samplings of 15 members. So smaller ensembles lead to larger uncertainty ranges on the risk ratio. And why this matters is we often use that uncertainty range to determine if our change in likelihood is, significant. So on the right, we're looking at percentage of land grid boxes where we find different attribution conclusions for different events or in different levels of warming. The darkest orange, we find significant attribution with both the 50 and 15-member ensembles. In the middle shade of orange, we find just with the 50-member, and we're also looking if we find in neither of the ensembles. What you'll note is there are lots of cases, in fact, sometimes over half of the land grid boxes where we find attribution with the full 50-member ensemble, but we don't find a significant attribution when we use the much smaller ensemble. And so this is most important when we're talking about smaller changes in likelihood. And so it can impact the attribution conclusion. And just to wrap up, to summarize the implications of what I've talked about here. So where models agree on the attribution of these larger scale precipitation extremes, and assuming we have confidence in these models based on where we can compare them to observations, then we can make statements about the possible effect of anthropogenic forcing on the precipitation extremes, particularly at the scales that we've talked about here. And this will add support and increase our confidence in doing attribution for more local events, more specific events. However, where the models do not agree, it will be much more difficult to find confidence for the local scale attribution. And then finally, understanding these model differences, including the amount of data being used to calculate the probabilities, this will help support the proper synthesis and comparison of different attribution studies and help us make sure we're interpreting them properly and then explaining what those results mean to others outside the community who care about them. So thank you very much.
Great, thank you, Megan. So did any questions come up in the chat?
I don't see any questions Probably if anyone have any questions, you can raise your hand and
So Megan, actually, if you want to bring up your slides again, I was wondering about the effect of ensemble size. I was a little bummed by, if you go to the earlier slide where, yeah, this slide, I was kind of hoping that, I mean, one of our hopes with these large ensembles is that, okay, you have a lower amount of warming, say at 1C, but because of the larger ensemble, you can get a clearer picture of you know, changes in risk ratio and so forth. And yet I mean, even though your next slide shows that there's some influence of ensemble size, it doesn't seem especially strong on this slide. Do you have a sense of like whether it would, if you could comment a bit on you know, whether it seems promising of like having massive ensembles that could actually tell us something more conclusive about the 1 Celsius changes?
Right, so there is a small difference between this slide and what we're looking at on the next slide, which I didn't get into, but here I'm just plotting the median. I'm basing on the median risk ratio for each of the ensembles. And when I'm talking about a significant attribution, I'm looking at that full 90% uncertainty range. So if I plotted here the lower bound or the upper bound of that uncertainty range, if I use that to determine the color shading, it would look a bit different here. But I think large ensembles are certainly very useful. I do think it is better to do event attribution with a large ensemble, with a larger amount of data. We're really we're asking about, you know, two distributions, right? A distribution with human influence and a distribution without human influence. And the more data we have to characterize those distributions, we're probably going to find that they're significantly different. And so I think that's where this is important, is that it really, you need to pay attention to how much data you have in terms of how you're interpreting this attribution conclusion. And particularly when you're comparing attribution conclusions between different models or between different studies that use different models or different amounts of data. It's saying, oh, well, this study found an increase and that study didn't. And there are lots of reasons why that could be. And one of those reasons is they may have had different amounts of data. So I do still think using large ensembles is very helpful for attribution. And while we're not seeing great agreement at 1C here, we're also only looking at certain events and certain spatial scales. And that doesn't mean necessarily that we can't have robust attribution in the current climate. It just takes a little bit more than pulling a grid box from this resolution of model.
Thanks a lot. So I think a question popped up in the chat. You want to read that?
Yeah. A question from Stephen Sovey. When you use regional approach instead of looking at single grid boxes, does that improve the signal enough when using this smaller 15 run ensemble size, or is the sample size more important?
That's a great question. Actually didn't directly compare which one is more important. In either case, you'll have larger uncertainty when you have uncertainty range when you have a smaller ensemble, and you will generally have larger uncertainty when you use a smaller spatial scale. But that's actually a good point to compare and see which one is more important. And no, I haven't done that.
All right, thank you very much, Megan. So we now have a quick poster introduction. We've had our first 3 regular oral presentations, and then we'll have a quick poster introduction from Xiaohui at University of Saskatchewan. So you can go ahead and share your screen and take it away.
Good morning, everyone. I will be presenting my poster to you. The topic of my poster is impact of future climate on extreme precipitation. This is a case study. Well, there have been lots of papers that have investigated the sensitivity of extreme precipitation to global warming. However, most of them have focused on statistical or climatological characteristics of extreme precipitation. Relatively less attention is given to the physical processes that by which the warming drives extreme precipitation changes in future climate. So this work, we will investigate the physical response of a single extreme precipitation event in a warmer climate. The case we selected here is the heavy precipitation event during the 2013 Alberta flooding. Well, this case produced more than 200 millimeter precipitation in southern Alberta and caused a severe flood at Calgary and the surrounding areas. So I think it would be interesting and critical to investigate how this event changes in a warmer climate. Well, the methodology we use here is the pseudo global warming method. We run two high resolution warp simulations under current and future climate. The control experiment just simply downscaled the ERA interim reanalysis, and the PGW experiment is forced with ERA interim plus a climate perturbation and the RCP 8.5 emission scenario. Well, this climate perturbation is derived from multi-modal ensemble mean. The models we use to derive this climate perturbation are listed in this table. So this models basically have higher spatial resolution and more ensemble members than other models in the semi-file project. Well, here is our simulation domains and the physics parameter resolution schemes. I want to go details. So let's move on to the results part. Well, this result, I have to say, is our very, very preliminary results. What I'm showing here is the 3-day accumulated precipitation. So overall, I think your WRF model did a great job in reproducing this heavy precipitation event in southern Alberta. Well, if we compare the PGW result and the control result, I think there are two major features I'd like to indicate. One is in this polygon region, we actually got increased precipitation in most locations. So out of this polygon region, we actually got decreased precipitation in eastern Alberta and western Saskatchewan over this region. This is definitely something we would like to explore in our future analysis. Well, this figure shows hourly precipitation as a function of time. This is calculated as area averaged value over this polygon region. Well, there are major two periods during which the precipitation increases, and at other times, the PGW actually has comparable and even lower precipitation compared with the control experiment. So that's it from me. Thank you all for listening. And if you are interested in this work, please go to my poster session tomorrow. Thank you.
Great, thank you, Shawi. So you said the poster session's tomorrow afternoon? Is that right?
Yes, tomorrow I think in the morning.
Tomorrow morning? Okay, great.
Yeah.
Yeah, so please look for that.
Thank you.
Okay, so we have then a few minutes break until the next speaker, which will begin, the next presentation will begin at 11:20. So please take a few minutes to stretch and relax, and we'll see you in a few minutes. And while we're taking a few minutes, do any of the speakers for the next half, do any of you want to test your audio or test your screen sharing before we proceed?
Can you hear me? It's me, Jonas.
Yes. Hi, Neil. Can you hear me?
Yep, I can hear you. Great.
Yeah, great.
If you want to, so Jonas Divicki, that's the pronunciation.
Yes, can you hear me?
Do you want to test your screen sharing?
But can you hear me well? It's okay?
I can hear you. Do you want to do any of you want to test your screen sharing?
Okay.
And I see Farshad is here. Do you want to test your audio or screen sharing as well? So Jonas, I currently see your web browser. And that's your slide, but it is it's with your notes as well.
What about now?
Okay, excellent. Yeah, that's the full screen. So you can just repeat that when it comes to your turn. All right. So you can stop your sharing.
Stop sharing.
Yep, that looks good. So how about you, Mohammed, Farshad? All right, Mohammed, if you want to start sharing your screen, then we'll be ready to go in less than a minute. All right, great. So welcome back. We will continue with the next half of this session. And our next speaker is Mohammed Ali Ben Alaya from Pacific Climate Impacts Consortium. Go ahead, Mohammed.
Okay. Can you hear me?
Yep, can hear you perfectly, and we can see your slides full screen.
Okay. Can you see my slide?
Yep, everything looks good.
Yeah, okay. So hi, everyone. Thanks. So today I'm going to talk about a new concept of max stable vector to analyze and predict the probability of precipitation extremes. So I will present the context, problem formulation, then the objective, and present solution results, and then I'm going to conclude. So the context of my work is statistical frequency analysis. And here we need for accurate estimation of the occurrences of hydrometeorological extremes. And the occurrences of extremes are often expressed in terms of return level value for a given return period. And the common use approach in hydrology and climatology involves the use of statistical inferences. So statistical inferences are probability claims about the process generating the data. So we say, for example, if we need to estimate a 20-year event return level, a 20-year events can be considered as the median of the probability of maxima of length of 10 years. So here we see the 20-year events. That's mean in a period of 20 years, there is 50 chance of an extreme event to be higher than the 20-year events. And also, if the variance of the 10 years, of the maxima of 10 years is very large, then this extreme event is gonna be substantially larger than the 20-year events. Assume now if you do have 50 years of annual maximum, and using 50 years of annual maxima, you will get only 5 value of maxima of length of 10 years. That means you cannot estimate the 20-year empirically. Five observation cannot estimate with occurrence. We cannot also estimate the variance of extremes. So to be able to quantify the uncertainty of empirical estimate, we have to be able to estimate the variance of maxima of 10 years here. So this, if you are, one issue is to take empirical quantile as references. When we take empirical quantile as references, while we don't know the uncertainty and the variance of empirical quantile, then we cannot characterize the uncertainty of empirical quantile. And in this case, we cannot use empirical quantile as references. In that case, what we need is to know is what is the variance of the probability of maxima of length of 10 years. But also we need also the variance of block maxima of higher than 10 years to be able to characterize this. So for the problem formulation, what we need is the picture, the relation of variance mean length as function of length of block maxima. And we need to determine what is the limiting distribution of block maxima when the length increases to infinity. For example, I show here from data from Victoria using 114 years, the standard deviation as function of the mean. We show here for the mean and the standard deviation of annual maxima. So if, for example, the variance increase as the length of block maxima increase, then the mean is going to increase faster. If the variance continue to increase, then the mean is going to increase faster. Another scenario, if the variance as the length of block maxima increase, if the variance decrease, then the increase is going to be very slow. And if the variance decrease to 0, then there is no increase. And in that case, the distribution will attain the bound. So this is the picture that we need. And this is the picture that can help users to evaluate and to choose the right and the correct design value. So the objective of this work is for a given block maxima from annual maxima of at the station of Victoria, we need to complete the picture of standard deviation as function of the mean for the block length, for a block maxima of length 2, 4, 8, 16, 18. And to do that, we're going to use additional information from a large ensemble of CAN-RCM simulation. So we gain an understanding of the law of nature by analyzing the simplest case and by leaving out our first attempt all intricate complications. So the best way and the simplistic way to solve this problem is to start with a straight line, with a linearization. And this linearization means on this space, that means the relationship between standard deviation and mean as length of block maxima increase is linear. So because of, we need to start with something. So the limiting form must satisfy the linearization, which is characterized by a concept called max stability. Actually, the GV distribution is the only distribution that satisfies the concept of max stability. Is going to help us to extrapolate, to extend the picture through the concept of max stability. So the GV has three parameters: a location parameter, a scale parameter, and a shape parameter. So the location characterizes the mean, the scale characterizes the standard deviation, and the shape characterizes the rate at which the variance increase with the mean linearly as the length of block maxima increase. So the GV distribution is commonly used as a tools for statistical inferences here. And to apply this GV for extrapolation, we need probability claims. And those probability claims can be found in the extra multiplicity theorem. This theorem gives us necessary and sufficient condition, which are IID, max stability limit exists, convergence exists, and as a consequence give us the GV. This claim gives us the condition to use this idea of max stability to solve the problem. So we can see here, for example, the GV fitted to annual maxima from Victoria. It helps us to extend the picture for block maxima equal to 1 here, block maxima with length 2 years, and block maxima with length 128 years. So we can see that the GV extends the picture using the stability concept. We see from observation, from observed data here, for maxima equal, for block maxima with length equal to 2. And we see here the standard deviation of and the mean of this value. We keep in mind that when we increase the length of block maxima here, we're gonna use the sample size that we use to estimate this value. Is gonna be the like here 60 approximately 65 value. So one issue with the regularity here is that the GV keeps the same speed as the length of block maxima increase. However, recently there are many anti-EVT papers, and the main issue with the application of the extreme value theory is that the condition to apply to the theory can never be checked. Also, the theory often involve waste of information by considering only extreme value. However, all this paper here fall in the statistical pitfalls to use empirical quantile that are with unknown, with unquantified uncertainty. That means they use empirical quantile without quantifying the variability of distribution with higher length block maxima. So extreme in nature, however, so why we need to use max stability? Indeed, extreme in nature are likely to be non-regular as well dependent. So then why regularity? In reality, regularity is useful to draw, even though globally is not regular, but locally it's gonna be regular. So for example here, let's try to apply the GUV locally. So we take here for annual maxima, we take the value standard deviation and the mean for annual maxima. And the point A2 here represent the point representing the value of standard deviation and mean for maxima of length 2 years. So if we take the GUV with starting here with mean equal to M1 and S1 and a direction going through the point 2, and then we evaluate the value of the standard deviation and the mean for block maxima equal to 2, we find this value here. And this value didn't match what we observed. That means, in reality, the GV distribution, it takes only one only one parameter. A direction alone that is given by the GOV is, however, insufficient. A direction as well as a magnitude is essential for the characterization of extremes locally. And thus we need to add an additional clue, which is the magnitude of extreme, to be able to characterize, to use the GOV locally. And here we introduce the local max stable vector. So let's see, for example, here in this situation, we can apply the local max stable vector here. And here, for each block maxima, we will assume that we are extending the picture at the same. We are extending the picture by assuming that the direction remains the same, but also the speed change at each level of block maximum. So this solution is based on statistical inferences. We use the idea of max stability and then apply that idea. However, the solution that we presented here is based on learning locally, and then use what we learn in order to put an assumption and hypothesis of how large the value get larger on how to extend the picture. And this picture here is based on statistical thinking, because I didn't make any claim about the process generating the data. So now we presented two solutions that are based on regularity. However, it is, however, impossible to be satisfied with an understanding of regular behavior alone. So passing from regular behavior to a behavior along a curved path brings new difficulty, and we must have the courage to overcome them if we wish to understand the mystery of extremes. So in our approach here, to extrapolate through a curved path, we're going to use additional information from CAN-RCM large ensemble. And our method here is going to use CAN-RCM large ensemble, quantify the net effect of the physical process on the direction and the magnitude using CAN-RCM4, and then assume the invariance of the effect with spatial resolution. For example, here we're gonna, if we do have 3 points here, block maxima with block length 1, and here block maxima with length 2 years, and block maxima with length 4 years. So if we calculate, we may calculate the impact of the physical process on this deviation here, delta D. We may also quantify the impact of the physical process on the magnitude of the vector. And given that information, we can use that information to extend to predict the value of the next point for the station, at the station.
Mohammed, I will need you to wrap up very shortly. We're getting to the time for the next speaker.
Okay, so for the data, I will show you now some result at the station of Victoria. So we see here the extension of the picture for 1 to 2, 4 until 128. So we use that value here, the standard deviation and the mean for block maxima of length 4 years. So the approach was helpful to predict that point here. So also,
I think I'll have to stop you there, Mohammed. My apologies. We are at 11:35.
Okay, so I will just
I sent you chat messages prior to at 12 minutes.
So this is the picture
sorry,
it was able to reproduce at many stations. So thank you.
Yep. So thank you, Mohammed, very much.
Thank you so much.
And I'm afraid we don't have time for questions, but hopefully you can put those in the chat. Mohammed can reply to them in the chat.
Yeah, thank you.
And we will, Farshad, if you're here, you can share your slides. Mohammed, you can stop sharing.
Hey, yeah.
And for our next speaker, Farshad Jalili Pirani from Western University. Please go ahead and share your slides and you can take it away.
Can you see my slides?
Yep, you can put them in slideshow mode, so it's full screen. Is it okay now? Yep, looks great. Thank you. Go right ahead.
Yeah, can I start or? Hello everyone. My name is Farshad. I'm a PhD student in civil and environmental engineering at the Western University under the supervision of Dr. Razan Najafi. And today I'm talking about compound flooding analysis over Canada's coastal zones. I'll be talking about the compound flooding, its definition or motivation, and then research methodology or study area data pre-processing and or flooding analysis, and then the corresponding results in the next section, and finally the conclusion. So compound flooding is when two or more flooding drivers happen together at the same time or with a short time lag, and it causes an extreme impact. So based on the IPCC, it has three definitions. When maybe one of the flooding drivers are like extreme flow, precipitation, and sea level. One of them is extreme, and the others are moderate, or when three of them are moderate, or when three of them are extreme. But in three cases, they cause an extreme impact. So in this study, in this research, we wanted to assess the spatial and temporal variability of individual and compound events, flooding events across Canada's coast. So Canada coastal areas have already experienced compound flooding because of the attack of the extratropical cyclones like Hurricane Dorian that caused 78.9 million damages in 2019 over Nova Scotia, or Hurricane Ian with 200 million damages almost at the same area in 2003. So in this study, we consider three types of data. One is a total water level, which is an hourly time scale, but we select the maximum daily to be matched with the stream flow data and precipitation data, which are in the daily time scale. So before we go to the main body of the research, we should do some we did some pre-processing on the data, like for each of these time series, we should have less than 20% missing in each year, and then 20% missing data in the whole time series, and we should have at least 80% overlap between three types of data. And then finally, we end up with a time period from 1960 to 2015 for our analysis. So we consider the extreme precipitation higher than 195, and we match them with the stream flow and total water level data within 1 day before and after the precipitation extremes. So our study area is the whole coastal line of Canada, which is the longest in the world, and over 7 million people are living in these areas. We have 41 locations, but we divided the whole area to three main regions, which is the Pacific, Great Lakes, and also the Atlantic coast. So for each location, for example, location number 1, we have those three types of data: total water level, stream flow, and precipitation. To do the flooding analysis or multivariate analysis, we need to create the joint or correct joint distribution of three flooding drivers or three variables, like total water level, precipitation, and stream flow. And this is done using the copula, which is a statistical approach that can quantify the dependence and structure of multiple variables. So true distribution is attained when we consider copula and also the univariate distribution of three time series. So in a bivariate case, on the figure on the right, we can see the joint distribution of temperature and precipitation as an example using the bivariate copula. But this is just to represent how it works. But in a three-variate case, we cannot present it visually. But in three-variate case, we have three dependencies between these three drivers. like the dependency between total water level and precipitation and stream flow, and total water level and stream flow given precipitation, which means that precipitation is going to affect the dependency between total water level and stream flow. So this is done using the C1 statistical approach. It can capture the true dependencies, conditional and unconditional dependencies between flooding drivers. So in our analysis, firstly, we just wanted to see that the joint distribution, we can see that the joint distribution of three variables is not changing with time. So from 1960 to 2015, the multivariate distribution of the PDF or CDF of three flooding drivers is not changing with time. Everything is fixed, both the univariate distributions of three variables drivers and also the dependence between them. So that means that everything is time constant. When we have the joint distribution, we calculate the parameters of this joint distribution using the Bayes theorem. So after this, creating this joint distribution, we just want to do the flooding hazard analysis. We do this using the concept of return period, which is the average recurrence time between the events. And here in this study, we consider and return period, candle return period, and or return period. We just present the results of and or. Anyways, and is when the three drivers are extreme. Candle is when the three drivers joint probability are higher, is higher than a specific level, and or is when one of the drivers, at least one of the drivers is extreme. Then using the failure probability, we wanted to see the probability of a potential flood event that happens at least once in a given project lifetime, and then we do some analysis using the CHR index, which is a component hazard ratio index, and this index shows that how the dependency between these three drivers is going to affect the 100 level return level of a stream flow, and divided this by just univariate 100 level of stream flow, or we can say that conditional stream flow, 100 stream flow divided by unconditional 100 stream flow. So moving on to our results, or stationary or time constant results. Here we are presenting the return periods or joint return periods for 41 locations. We present here the median and also the uncertainty of the joint return period. We can see when we have dependency and mostly the positive dependency between drivers, then the joint return period is higher than the independent condition and also less than univariate. So this highlights that the flooding hazard should be considered in multivariate case, and somehow the univariate is underestimating the flooding risk. So this is more highlighted for both Pacific and Atlantic coast. We also have some locations are the Great Lakes area. So regarding the and return period, we just wanted to be selective and we just focus on the locations that out of three dependencies at each location, two of them should be positive. Then this location is considered as a critical location. So based on this dependence, considering dependence between them and calculating the and return period, we can see that how this dependence, joint return period is lower than the independence case. And again, it means that the implication is that if we are going to do some designing what around the coastal areas, it should be based on these new results, considering the dependency between the flooding drivers. And the results of CHR index, again, for 41 locations shows that at locations that we have positive dependency between drivers, this index is higher than 1. For example, in this area in the blue region, we can see that it's higher than 1 over the Pacific coast, and it means, or location, for example, 41. And it means that there is some kind of dependency which is affecting the stream flow, like stream flow given total water level and precipitation, both precipitation and stream flow, which causes the backwater. That means that the univariate return period, if we can, for the stream flow, if we consider that is not that much correct, and the total water level and precipitation are affecting the return levels of stream flow. So on the non-stationary flood risk analysis, we consider that the joint distribution of three drivers is changing with time from 1960 to 2015. So this change can be both in the univariate distributions or also the couple of parameters or the dependence parameter between these variables. So we fit a different models, stationary, linear, and polynomial models to the dependence parameter and also the location parameter of the univariate distribution of the drivers. And I just want to see that which model is the best fit, or if it is time varying, which model can capture that time varying behavior, linear or polynomial. Then later on, using WAIC metric, we select the best model. So here again, we just wanted to be selective. We just wanted to select the locations that are critical in this regard, like the situation of the flooding is getting worse in future or by passing time. So on vertically, we have the coupler parameter or dependence parameter and horizontally, we have the location parameter of 3 time series. And if at one location, 2 of the parameters has a decreasing trend, or 2 of the dependencies has also decreasing trend, then we try to discard that location. We just focus on the locations that the situation is, the locations that are really critical regarding compound flooding. And after all these filtering processes, we ended up with 23 locations. And for these 23 locations, we repeated the analysis in the stationary process using the same methods like return period and CHR index and failure probabilities. So out of these 23 locations, at 17 locations, we can see that with increasing the dependency, or especially the positive dependency between the flooding drivers, the joint return period is decreased from 1960 to 2015. And at the locations like six other locations, we can see that there is no change in the dependency between flooding drivers, but we can see that at least one of the flooding drivers is time varying, or the return levels is increasing. So both of these means that if we consider 3 fixed return levels for 3 variables, then those 3 return levels has a lower return period in 2015 in comparison with 1916, which means that if we don't consider that, we are again somehow underestimating the flooding risk. So here we are presenting non-stationary analysis of CHR index. Again, we can see that between 0.4 to 4.5% increase in the CHR index at those 23 locations, like for example, location number 2, location number 41, and some locations that are critical also at the Great Lakes. And again, this increase in the percentage change in the CHR index is because of the considering the dependency between the flooding drivers. It means that this CHR index, or if the stream is getting affected by the total water level and precipitation, it is not fixed. Even this dependency is changing over time. And here we are presenting the results of failure probability. So we can see that with increase in the lifetime, the failure probabilities are increasing, or hydrological risk are increasing. And when we increase the return period, this failure probabilities decreases. So in the multivariate case or 3-variate case, in comparison with the univariate case, we can see that 3-variate failure probabilities are higher than when we consider just one variable like precipitation, a simple or total water level. So yes, it's correct that we consider the dependency, but when we consider that time varying behavior in the dependency or change in the dependency or the return levels of the 3 drivers, then again, this has a higher failure probability than considering the dependency, but no change in the dependence or marginal, or the univariate distributions. So the situation is more important when we consider the non-stationary behavior of the 3 drivers, both the dependency and the location parameter of the 3 drivers. So this, moving on to our conclusion section, what we found in this research is that the interdependency between these flooding drivers is really affecting the joint behavior. And if we can say we ignore this dependency, and also if we don't consider that, we are somehow underestimating the flooding risk, as we saw that the 3-variant return periods for and are lower than the univariate. And also when we consider non-stationarity in the individual flooding hazards, and also the dependency between them, we can see that flooding risk is increasing our half of the locations. This is more important over the Atlantic coast because they experience a lot of tropical cyclones, extra tropical cyclones each year. And so these tropical cyclones cause at the same time, extreme precipitation, sea level, and that causes the higher dependency between these flooding drivers. And
thank you, Farshad. I think we are beyond the time for your presentation, so I'm sorry I'll have to stop you there. But yeah, please, the audience can look at the remaining conclusions. If they have any questions for Farshad, please post those in the chat and Farshad can respond to them there. I'm going to stop your sharing, and then so we're going to move on to our last speaker for the session, Jonas Dibicki from Environment and Climate Change Canada. I can see your slides. You can put those in full screen. Excellent. Everything looks good. Please take it away.
Very much. I would like to acknowledge the co-authors, Lauren Durham, Spiros Peltaus, Daniel Peters, and Barry Bonder. So the title of the study is an assessment of open versus ice-affected peak water levels in selected Canadian rivers. As you know, in Canada, most of the rivers are ice covered for a significant part of the year, maybe between 2 months till 8 months. And the high water level related to this ice-affected season is sometimes higher than the open water seasons. And that's what we would like to analyze. So the objective of this study is to compare the annual maximum water levels occurring during the ice-affected and open water seasons. And we use 151 Water Survey of Canada stations from the recently released Canadian River Ice Database. And the time period of analysis is between the recent 30-year period between 1985 and 2015. If you look at the rating curve, that means the stage discharge relationship in a river, the bottom line, this is just an example of a specific river. The bottom line shows the open water rating curve. That means the relationship between discharge and stage is shown by this line, and it's usually a stable line as far as the station is stable. But the circles shows here are the stage discharge relationship observed during ice cover season. So the black circles represent the breakup period. That means when the water level associated with river ice breakup, and these open circles are related during the freeze-up period. So obviously these stages during ice period are much higher than the open water season. And this is as a result of usually during breakup. This is an example of a breakup where there is an ice jam over here. And because of the breakup ice jam, there is an elevated water level because of the backwater. So when this line is the open water related to the open water, and the other would be because of the ice jam, the elevated water level. So we consider this. These are the stations included in the Canadian River Ice Database. In general, the Water Survey of Canada has over 2,800 gauges. But this database contains data at 196 selected stations. And from this, we use the criteria at least out of the 30-year, 50% of the year, there is a high water level data. So because of this, the total stations used for this analysis are reduced to 151 stations. So if you look at the water level in a given water year, this shows the water level evolution throughout the year. So this is the first part is just open water season in the fall. Then the first B date is when the first ice affected water level started. And this HF shows the freeze up. During freeze up, the water level rises immediately when the river starts to freeze up. Then there is a dip in the water level because of hydraulic storage, and then it stabilizes, and you will see a decrease in water level because of recessions throughout the winter season until a breakup start during the spring, which will raise the water level, and we may most probably get the maximum high water level. And then the last bit, the last ice affected water, then we'll go to the open water season, where we'll get the maximum of the open water season. Sometimes in the middle of the winter, if there is a relatively warm weather, there could be midwinter breakup events. So if you look at the occurrence of ice affected peak water levels, so this diagram shows us at each station the proportion of the years with a specific type of breakup. So as you can see, the spring breakup is dominant in most cases, which is covering around more than 70% of the time. Ice affected high water level results from spring breakup, but there is also a portion which can occur during the freeze up or midwinter breakup or secondary freeze up. So these are just the different ice affected high water levels. To do the analysis, we have converted first the water levels into water depths, nominal water depths, because it's much better to compare, since most water levels are from assumed datum. It's much better to compare with nominal water depths. So this is just to convert the water level into water depths, then all the analysis will be done through using the water depths comparison. So what we do, we use the Weibull floating position method to rank the water levels and calculate the return periods, and we compare the return period between ice affected water level and peak water level and open water peak water level. So when we do this return period analysis, if all ice affected peak water levels return periods are higher than the open water, we call that station ice dominated. If the open water level is higher than the ice affected water level return period, we call it this open water level dominated station. While if there is an overlap between these two, we classify it as a mixed regime. So based on this criteria, out of this 151 stations, as you can see, all the red circles represent ice affected, ice dominated high water levels, while the blue represents the open water dominated high water levels, while the greens are mixed regimes. So in terms of percentage, around 29% of the stations are ice dominated and 26 mixed. So in total, the mixed and ice dominated regions constitutes around 55% of the stations, while 45% of the stations are open water dominated peak water levels. And the regional distribution shows some pattern, while the interior cold regions are mostly ice affected and mixed regime dominated. The coastlines, more in Quebec and in BC and part of Alberta, they are the high water levels are open water dominated. So this is just to show that the proportion of ice versus open water dominated at each station. So even at a given station, even some years are ice dominated, other years could be open water dominated, and this shows the proportion. Again, in the interior regions, it's mostly ice dominated high water levels we get, while towards the coast, it's mostly the open water dominated. If we plot here the ratio of ice versus open water levels and the discharge ratio, this clearly shows that most ice affected water levels, this below 1 shows that they are at a relatively lower discharge but higher water level, and the 3 regimes are clearly shown in this map. And if we just calculate the difference between mean ice maximum water depths and mean open maximum depths, this shows for 151 stations. So all these red regions shows where the ice affected water level is higher. Here is where the open water level is higher, and the mixed regimes are in the green. So however, there is some uncertainty in our result, and which mainly come from the reason that this breakup events, especially the spring breakups, are very violent events, and usually they affect the measuring stations, and sometimes data will be missing during that critical time. And if we plot the number of missing data from our 30-year record, as you can see in these regions where we don't have breakup water level from 1 to 4 up to here 11 to 13 years of data missing. That means that's because of during the breakup events, instruments are destroyed and we don't have that important data for that yet. So this could affect our result to some extent because there will be bias towards the open water level. So this is the 151 stations with the criteria. We have 50% available, but if we increase the criteria to 20 years out of the 30 is available, the number of stations we will have will be reduced. If we say 25 years we need data, then the number of stations reduced to 85. And the number of stations with complete data, that means 30 years of both ice affected and open water, peak water level, the number of stations is reduced to 20. So maybe this lack of missing data during high water seasons can affect our result to some extent. This is just to show the distribution of these water levels for these two type of regimes. In those stations which are ice dominated, you can see that the ice distribution of ice affected water level is ahead of the open water season, while for the stations which are open water dominated, the distribution is clearly shows that water levels associated with open water season are ahead of the ice affected water levels, and these are for the mixed regimes, the overlap between the two distributions. So as a conclusion, the results show that around 55% of the stations are ice affected, peak water level dominated, while and mixed regimes, while 45% stations are open water, peak water level dominated. Stations with predominantly ice affected peak water levels and mixed regimes are mostly located in the cold and continental regions. And of those ice affected peak water levels, most, around 73%, occur during spring breakup, while the rest occurs during the freeze up and midwinter breakup seasons. And we have also tried other alternative region classification methods based on the overall maximum water level, or based on the number of years with high water level, and we got a similar result to this one. So the next step is we would like to examine even further the extent to which data quality has affected peak water level region classification results. And also, ultimately, we want to look at the impact of the potential impact of climate change on affecting this regime, ice affected versus open water peak water level. And to do that, we are looking at a different time window towards the past and also longer time windows to get a much robust results. So thank you very much. If you have questions, you are welcome.
Thank you very much, Giannis. So we are at the end of, beyond the end of our session time allotment. So I want to thank all of our speakers and thank the audience members for their questions as well. I'll leave the meeting open in case anyone wants to respond to questions that have been posted in the chat. I see there are a couple of questions.
Yeah, there are a couple of questions. So should I go ahead or, I mean,
Yeah,
Yeah,
can answer them for me.
Yeah, so I mean, we have I guess just as a program note, we have our second extreme precipitation session starting at 2:55. So please join us for that. So yeah, I mean, it's the lunch break now, and anyone who needs to take off can do that. We can stop the recording, but yeah, if maybe one question you want to read from the chat and we can address that.
yeah, one question from Mindy to Jonas is, how are you including smaller streams and rivers that sometimes freeze up from the bed and then overflow midwinter, such as in the Caribou of BC, that happens periodically, causing bad midwinter flooding? Since this will become more common with warming in currently cold areas.
Yeah, I mean, we use different criteria in selecting stations from throughout Canada, and we have stations with midwinter breakup included in this study, and that's why if you look at this graph, the yellow shows the midwinter where midwinter breakup is actually the dominant high water level. That means at least 10–15% of the stations are midwinter breakup dominated. And our some other studies we have published show that the frequency of midwinter breakup is increasing in the future, and that could be revealed in our other study we are doing, where we do this same analysis in different windows, so that in different time windows, 30-year time windows, so that will tell if there is a climate change impact on the frequency of midwinter breakup events or spring breakup events or off water season. That's still under investigation.
Yeah, very interesting how that can be quite counterintuitive, right? Because you might just expect less of an ice impact with warming, but then the timing of it shifts to the midwinter potentially. So very interesting.
Exactly.
Yeah.
Actually, very clearly, the data shows that the frequency of midwinter breakup the last 30–40 years is increasing. The number of events associated with breakup.
Yeah, thanks. There is a quick question from Yetian Lo. What would cause some rivers to be ice dominated and others be open water dominated?
Yeah, it's so many different factors affect that. One is, of course, the hydroclimatic condition in that particular station, but also the morphology, the geography, the elevation, all physical characteristics of the region. So geophysical characteristics and hydroclimatic characteristics, this at the end determine whether a given station is ice dominated or open water dominated.
Great, thank you, Jonas. Very interesting work, and again, thanks to all the speakers and to the audience members for the questions as well. So we hope to see you again at 2:55 for the second part of this session. Have a good lunch.
Thank you very much.
Okay.